Okay, then we can start for today. I would like to make some correction. I made a mistake the other day with an example. I just noticed yesterday when I was going through the notes randomly, and I noticed that something I said about an example made no sense. So it was this example. I forgot what it is. I think it's exercise 3.16. I changed it, so now it should make sense. So it was this ring. Let's say Fp. It's just a circle. Sorry. So it's just a circle over Fp, and so especially during the lecture, I put brackets here, but that made no sense because this is a unit in that ring, right? And so I meant to sort of cook up a local setup, but I said that in the lecture. I think in the notes it was fine. But yeah, so the point is that for this ring, what I want you to prove is that this thing here is free all the time. Actually, it's free. It's not just locally free. It's just free if and only if P is not 2, right? You can see that if P is 2, this is not even reduced, right? So because then this becomes x plus y squared minus 1, and it's actually all x plus y equals 1 to the square. So it has it's essentially isomorphic to a line, like a thick line, whatever. And however, so has a p basis if and only if p is congruent to 1 mod 4. So you may have that this is free, but the existence of a p basis is a subtle thing. And so here the point is, like, I wrote it down like that, but the whole point is that -1, let's say the square root of -1 exists in Fp. That's what you really want. And these two are equivalent conditions, but what you need is this. Probably you have seen this before, right? Like -1 has a square over Fp if and only if p is congruent to 1 modulo 4. And so you can see that this is what you need, for example, because if you have the square root of -1, then this quadratic form here, the form as a product of 2 lines. Because then you can write -1, let's call this I, and then this is x minus 1 times x plus y, but with an I over there. But it's the product of 2 lines equals 1. And so this becomes isomorphic to a line with the origin removed. And so we know the p basis exists there. We have seen that, but the interesting part is 0, 1. So, but it's an exercise for you. I just wanted to make that correction because, well, if I made a mistake, I should correct it. Okay, so any questions so far? So the other day, we started to do a whole bunch of fun things. In particular, we started to talk about matrix duality, which is this beautiful duality that happens on complete local rings, right? So recall, if you have a complete local ring, let's say equicharacteristic, complete. In other words, we have an honest singularity, right? Like, that's the way we think of a singularity. We think of a singularity as a complete local ring with residue field K. This is a equicharacteristic, then automatically it becomes a K algebra, right? And so in here, we can cook up an injective hole of the residue field. So technically speaking, we should put so it depends on R and K in principle. So injective hole of the residue field. So I would like to start today by making the remark that even though this may look strange, it's a very explicit object to play with. So the virtue of this thing is that it lets you do computations. So, let's recall what math already was. So out of this thing, you can extract a functor D, which is dualization. And what you do is that you home into E, and since E is injective, this functor is exact. It's contravariant, and so what we saw is that it is an autoequivalence between Noetherian modules, in other words, finally generated modules, because we work over theorem ring all the time. And so you get Artinian modules. And so Artinian modules should give you a computational flavor, right? So very often they are things like a finite length, which means that there are k-vector spaces. And so you can do computations, like linear algebra, compute dimensions and things. So this is more the computational side. And so the Noetherian side is the conceptual side. Here's where you want to have your thoughts. This is where you want to do your computations. That's sort of the idea. And so, but the point is that these two things are anti-equivalent by matrix duality over a complete local ring. Okay. Any questions with this? We're taking this as a little black box, essentially. But the key point actually is that, so for this to work, it relies on the following. So this is what is at the core of this. The point is that the endomorphisms of E, it's canonically isomorphic to R. The only endomorphism of E is multiplication by an element of R, a scalar multiplication. All you can do is scale E. That's it. It has a very simple structure as an R module. So actually what happens more generally, and this is important, is that this is isomorphic to the completion of R. So we're assuming that R is complete, so that we can say at this step that this is just R. But what that means conceptually is that you can define this E over any local ring. But when you do that, it is automatically an R hat module. You see? Because there would be a linear action of R hat on E. Right?
Mm-hmm. So in other words, if I take any comp of like an automorphism, that means that it's isomorphic to the completion of R.
So here we're taking arbitrary homomorphisms. So in particular, like actually we're gonna see this in a sec. E can be killed by a lot of things.
Oh, okay.
So actually it has a very specific subtle. So it's not true that any map here from here to here is gonna be an isomorphism. And actually we're gonna try to pay attention to those elements of R that kills E.
Okay, I see.
For example. So, but yeah, so the point is that when you have R and R hat, and so the point of this too is that if you have E over here, it equals E over here. So what this means is that if you have the injective hole of K over R, remember that R and R hat, they share the same residue field. So here you always have an equality. Okay? Because of that, if you define it over R, it automatically extends to R hat. Okay? We're gonna see that with an example in a sec. Okay. So how do you compute the injective hole? It's not difficult actually, and it's a super explicit thing. So let me give you an example of how this works. Example. What is the important ring here? We can take R, Well, it has to be a local ring. So we're going to take polynomial ring. Let's take it like this. But, so by what we were just saying, in principle, we could just take this too. So it's the same example. And we'll see actually, in this example, that I can define it over here, but it automatically becomes a modular power series ring. So, in this case, we can define E to be the following. So it's going to be a direct sum. It's going to be a vector space over K. It's going to be, yeah, it's going to be a free vector space over K. So the basis, I'm going to denote it like this. I'm going to take monomials, but I'm going to take them to be negative monomials with negative exponents. So I'm going to take objects like this. And I'm going to take this to go from here to here now. So all I need are these monomials to always be positive. Okay, that's what I mean here. So, okay, and actually, there is a very important element here. It's the first one here in the direct sum. Let me put it like x1 through xn. So it injects here. It's one of the direct sums, right? It injects and it projects onto it. And so, well, this is just a copy of K, right? This is a copy of K in which 1 goes to, let's give this object here, this symbol, a name. It's going to be denoted by U. You will see why in a sec, okay? So this is just another copy of K. And so this E here is an extension of K. That's the way to think about it. And what you do is that you extend it so that it always makes sense to multiply by elements here. That's what it is if you think about it. So look how extended it is, right? As a K vector space is this. So K sits as the first direct summa, and then actually the idea is to start adding direct summa so that you can introduce another module structure here in a minimalistic injective way. So what is the R linear action? So R linear action, what you do? So if you have xj, an element of R, right, as an element of R, you want to multiply by a monomial like this. And what this is, if you want by definition, well, it's what you think it is. Actually, there is not much of a choice here. J, E, J minus 1. You see, it's what you think it is, right? Like you just cancel the xj. In if ij is more than 1, but you're forced to be 0 otherwise. Oops, sorry, this is one table. So you're forced to be 0. It's not too much of a forceful thing. I'm not forcing anything. I could have just said, another way to think about it, another way to think about it, if you go back to this direct sum, I could say that the other direct sums in these counterpoles are just 0. That's what I could have said. And so you see, because if ij is just 1, if ij is just 1, when I multiply by that, I'm just forced to land into the 0, 1. So it's just that. Okay. And in particular, so the point is that if you take a monomial like this, just look at this monomial. This would be annihilated by actual monomials in R of sufficiently large degree. Because if you start multiplying by something like x to the n, you know, like j to the n for this very large, eventually you will pass the exponent of xj over here, and then you are 0. Okay? And if you think about that, what this is telling you is that automatically you have an action, automatically this extends to a unique, actually, R hat action. Okay? What is the point? The point is that R hat it's going to look like power series, right? And so I'm gonna go and put a power series here. But for all sufficiently large monomials in that power series, they're going to kill that element. So most of them are going to act like 0 for most monomials, and that's it. Okay. So you see, so one second, you see directly that these two things are the same. Yeah.
So I got a little bit lost. So how do you go from so what's the action on so the action is on our power series or is it in the
no, it's gonna be R hat acting on E.
Oh, okay.
So here I'm telling you what is the R linear action. So there will be an R module structure on E. As I define it, E is just a K vector space. That's the only structure I gave it, you know, by writing it down like that. Now I'm telling you that there is an R linear action which is given by that. So here it suffices to say what is the action of xj, and you extend by linearity and compositions and so on. And it's just this. So the R linear action, I hope it's like clear what it is. But what I'm saying is that you see that all sufficiently large degree monomials will kill this element. They will act like 0. And so when you think about it, what that's telling you is that if you can also put there a power series action, which is going to be this infinite sum. Yeah. But the tails are going to act like 0 on any given monomial.
Oh, okay.
So the action is already there automatically. Yeah. And so you can look at this example and you can see super explicitly this phenomenon, which you may think is mysterious, but it's not so quite. Okay, so something you can do is an exercise here is to check that this is indeed an injective pole of the residue field. It is an injective module, and it always intersects. Sorry, any submodule of it has to intersect K non-trivially. And you see why, right? Because by this R linear action, any given monomial, a multiple of it, is going to be part of this direct sum here. So you can see that you can construct an injective pole of the residue field extremely explicitly. That's the whole point. Okay. It's nothing mysterious. It's supposed to be non-mysterious and explicit. Okay. Yeah, it's just like I think the first impression you may have of the injective pole of the residue field is it's like a very mysterious thing. But I would like to say it's not. Okay. Okay, let's write it down again, right? So to be an injective pole, it has to contain K, right? We just saw that. So this is K, and you have this formal generators, if you will. Okay, so these exponents are positive. This is E, right? And so what is this containment? You take 1 and you send it to U. And so I would like to emphasize the importance of this. This direct summand here, this first direct summand here, it's very important. And but it's K inside E. And this U here, it's a very special element. It's called the Sokal element. The Sokal element. Why it's called like that? Because if you compute the Sokal of E, so let's say the Sokal of E, what is the Sokal? Well, it's given by the elements of E, let's call them epsilon, such that they are killed by M. More conceptually, you can think of this as the set of Homs from K to E that are linear. In other words, is the dual, the matrix dual of K. That's why the Sokal is important. It's right there. It's the dual of K. And what you think it is? Look, these are all the elements that are killed by M. Who is killed by M in the Sokal? Who is so sensible that if it is hit by a variable, it vanishes? It's you. It's the only element. So only things that are K multiples of this have that property. Right? Because take the definition, right? It's just this huge direct sum. But if you leave here in sufficient large degree, if you're hit by X, nothing happens to you. If you're hit by a variable, right? Because your exponent is large enough to support the non-vanishing. But if your coefficients here are exactly 1, then if one of the variable hits you, then you are 0. Right? So you will see that the Sokal is none other than K times U, this direct summation, which is the copy of K inside E. In other words, K is self-matrix dual. The matrix dual of K is itself. Gotcha? And yeah, you see that, and you see this. This is why this is called the Sokal element. In general, the Sokal of an injective Hall of the residue field is K, and any generator there is called a Sokal element or the Sokal element. Okay. So this element is going to be important soon. But before we get into that, so well, that was the Sokal of power series ring. But what about the Sokal of what about the injective Hall of any complete local ring? How do we compute an injective Hall of the residue field? So, yeah. What if R equals, let's say K, which by the coherent structure theorem is to say that R is a complete local ring, right? How do you compute? How do you compute the injective Hall of the residue field if you have an explicit presentation like that? And actually, it's not so difficult to see what it is. So it turns out that you can take E, maybe let's call this A, okay? And let's call this ring here R. Okay. You have R modulo A. And so how do you compute this? Well, it's actually, if you think about it for 5 minutes, it's actually going to be obvious what it has to be. So I'm going to get you the recipe. So what you do is that you're going to take, so here now I'm going to look at the injective Hall of R, which I just told you how to compute, right? Is that huge direct sum? So you're going to take the elements in there, and you're going to look for those that are killed by A. Since they are killed by A, they automatically become an A module. Because A is R modulo A. They're an R module, they're killed by A, so they automatically have an A module structure, right? So it's gonna be this, and this is none other than actually hum from R A to E, right? Because A is a principal R module. So to define a map from here to here, all you have to do is to decide where one goes, which is the choice of an element here. But you have to make that choice so that it happens. Right? And so if you will, the injective hole of K over A is the matrix dual of A. Okay? It actually generalizes this property here. It's a generalization of that, and you can prove it. This is something you can check directly. It's an exercise. This module here, well, it's automatically an A module. It is injective, and it is an injective hole of the residue field as an A module. Okay. And actually, well, it's hitting you in the face. The subhole of this thing, it's also K. Notice that it's the U is gonna be here because the U is killed by M, therefore it's killed by A because A is inside M, and so on. So this thing here is still K times U, and so this the exact same U. It's also a subhole element. It's a subhole element. So you agree that you can be very explicit about what injective holes are? And they are K vector spaces with very explicit bases. And so the cool thing about them is that they're very suitable for direct computations. Okay? If you need to. But here is one more thing about them that we are going to need. Here's an exercise. One more thing about them is that if you have a map from E to any other module, let's call it Phi, this map is injective. Well, there's a direction that it has to be phi of U, the subhole element. So the U is inside E as a subhole element is non-zero. That has to happen, right? Because it is injective. It cannot vanish on a non-zero element. And the subhole element is non-zero. It's K inside E. Right? But the converse is true. And that's one of the wonderful things about the subhole element. Okay, so probably from last time you see that it is very important to tell when a map from E is injective. And so it suffices to verify that the subhole element doesn't vanish. And why is this true? Why is this true? Think about it. Just take the kernel of phi. The kernel of phi, if it is not zero, right, it has to intersect K non-trivially because E is an injective hole of the residue field. It is a hole, the whole part is used there. And so it has to, so a multiple of U has to be there. And so U has to be there. So phi of U has to be zero if it's not injective. Right? So, okay. And so, for example, last time, we had the following theorem. Last time we said that if if you have any algebra S such that R is complete, we had an equivalence of the following notions. The first notion was the notion we wanted to understand: purity. Theta is pure. Well, if theta is pure, then eta E, injective of the residue field to S tensor RE is injective. This one is obvious, right? Because purity by definition means that the same is true. The same injectivity is true for all n, not just E. So that one is sort of trivial. And well, the third condition we had is that theta is split. So this direction here is obvious, but the amazing one is this one. That just because E is surjective, theta has to split. Okay? But actually we can add a new condition here, because the injectivity of this map means that the image of the Sochel element is not zero. But what is the image of the Sochel element here is one tensor U. So in other words, one tensor U in this module is not zero. That's gonna come out later. So it's important to have it here. So to prove that theta is pure, all you have to do is to verify that this element is not zero. Okay. And what was the proof we had for this? It was a really, really cool proof. And because it has a remarkable, well, it uses the following. So it was based on, so the proof was based on taking eta E and computing its matrix dual. And what was the matrix dual of eta E? It was a beautiful map, right? It was the trace of R. What the trace do? It takes a map sigma here and evaluates it at 1. So if this is injective, this has to be surjective, and the surjectivity of this is by definition splitless. That's it. And actually, if S were finite, these two things will. So they will be matrix dual to one another. So this eta E and the trace are matrix duals to one another if S were a finite or module. Okay? You remember that this was a proof. Now, what do we want to do with this? So let's make it here as an observation. It's a corollary or from the proof. So with the same hypothesis, but now assume that S is finite. It's a finite generated R module. Then you can prove out using the exact same proof that the trace of M is matrix dual to eta of dm. What is this? This is a map from the dual of M to S tensor the dual of M. So this is a very important conceptual object to understand, the trace of a module. Here is where our ideas live. But in practice, when we want to do computations, this is the object that's going to be important. Okay? And so you will see that the surjectivity of this For example, if we want to understand, it's going to translate into the injectivity of this, and so on. Okay, that's all good. So what is the first theorem we have? It's just that over a complete local ring, purity and splitness are the same notion. Okay? It's a wonderful thing. Over a singularity, an honest singularity, a splitness and purity are the exact same thing. And it has the following wonderful corollary. Corollary, take a finite algebra. Finite algebra. Remember that this means that S is a finally generated R module using restriction of scalars. Okay. Then, if theta is pure, implies that it is split. And of course, you can add the other direction. So this is the other case in which purity and splitness happen to be the same thing. If the target of the map happens to be finite, if you have a finiteness condition here. So how do you prove this? Well, you want to prove that theta is split, right? So we want to show that the trace of R is surjective. Is surjective. So because this module here is finally generated over R, what is the first thing we can do? We may assume that R is local because we can localize, and localization is a flat operation, and since this is finally generated, it's going to commute with hum, right? So the first thing is that we may assume that R is local. Because given the hypothesis we have, the localization of the trace is the trace of the localization. This is not true if S is not finite. You remember that from previous lecture that we were discussing that? So this is where you use finiteness to do this localization step. Okay? And once you are in the local case, well, you can do another faithful flat base change, right? So okay, remove this. Moreover, since R to R hat is faithfully flat, in other words, it preserves surjectivity, but surjectivity can be checked after completion, right? And so in this step again, you need that S is finite. The completion, well, this not the completion, but the base change by the completion of the trace of R is the trace of R hat. This uses that S over R is finite. It's finitely generated. Okay? Remember that Hom is not, it doesn't commute with flat base change unless the source of the Hom is finitely generated. I want to stress this so much. Okay? I don't want you to make a mistake in one of your papers by commuting base flat base change with Hom without assuming, without checking or having that your sources have an error. Okay? It's a common mistake. So, you agree with this? Yeah, so this uses that S is finally generated. Actually, it also uses that S is finally generated to say that S tensor R hat equals R hat. No, this is done, yeah. Okay. So because of this, what is the conclusion? We may assume that R is complete. And so we are done by the previous theorem. I don't know if we call it theorem or proposition or what, but let's call it theorem. You see, by using that S over R is finiteness, you can just reduce to the complete local case where it is just true, because it's true. Right? Any question with this? And this has another corollary. And I ask you to be patient. We're gonna put Frobenius here, and in a second we're gonna see the beautiful consequences of this, of all this general stuff. So corollary. Let's take an algebra over a local ring. An algebra. So here we are not assuming that it is complete. Okay, we already did the complete case. Let's take E to be the injective hole of the residue field, and let's take U to be the Stoffel element. Okay. Remember, the Stoffel of E is just a copy of K inside E, and U is any generator. And you can be super explicit about it if you have a presentation. And so then the consequence is that the following are equivalent. The first one is what we want to understand is when exactly this math is pure. Pure is actually a cool word, isn't it? Sorry, definition. What is pure? Well, B is that eta E from E to S tensor RE is injected but let me put it over here so that I have enough room. i.e., one tensor U inside S tensor E. You see, what you did is that you base change the injective hole of the residue field, and you look at what the Stoffel element goes to. If it doesn't vanish after that base change, this map eta E is injective. So the point is that the Stoffel element is a survivor of phase change. Okay? And C is that the completion the completion, yes, of theta, which is not the same thing as base change by the completion, because S is not being assumed to be finite as an R module. Is the completion, the completion functor. So R hat, S hat is a split. Well, in this case, we saw that it's the same thing as purity. Because if R is complete, then these two things agree. So purity of a normal map, or just a map, it is equivalent to the completion splitting. So the completion is only granted. The splitting is only granted after completion. Okay? Let's see. What's the only thing here that is not? What do we have to prove? What is not obvious? B to C is not obvious. You're right. And then the C implies A. So let's do that. Let's start with B, C. Yeah, B, C. Actually, let's prove that B and C are just equivalent. Just B equivalent to C. The proof is the following beauty. Okay, proof. So it is a proof worth having in your heart. So what we're gonna do is to compare eta E and eta E and the eta of the completion. Okay, so in principle, we have to look at eta E, which is a map from here to here. Let's just put it here, eta E, right? But around here we have S hat, tensor, R hat, E. So the injectivity of this is B, and the injectivity of this is C, right? By the corollary. Are these two things interconnected? You may ask. Well, yes. Yes. Because the injective Hall of E and the injective Hall of R hat, sorry, the injective Hall of K over R and the injective Hall of K over R hat are the same object automatically. Look. I can just drop the R hat from here because what I just said. And under this identification, this map here is just what you think it is. It's just the, what am I doing here? It's just E tensor S to S hat. But S to S hat is what? Is faithfully flat and therefore is pure, and therefore this map is injective. There you are. This map here is injective, therefore eta E is injective if and only if, so is eta E hat. There you are. That's why B and C are equivalent. Because of this diagram, which makes sense because when I was telling you that the injective Hall doesn't see completions. It's just like this fuzzy thing going around. Okay? So the consequence is that eta E is injective if and only if, I don't know why I call it eta I hat. How can we call it? What is the name of this? Well, I guess the orientation is bad because it's bad and good. It's good because what I was telling you, this thing is essentially that up to this. But the issue is that we don't write like in principle this depends on R, right? But let's call it tilde here. Eta tilde E is injective. But eta I tilde eta I is the eta I that makes C works. Okay. So B is equivalent to Z. That's the whole point. Okay. Any questions with that? It's a pretty proof. Okay, if there are no questions with that part of the proof, let's prove that C implies A. In other words, that if you have a splitting after you complete, you can for sure guarantee that your map is pure. You cannot say this is split. The split doesn't descend. You know, the splitting is an infinitesimal thing that doesn't spread, you know, to the whole thing. Okay, here. Okay, let's see why on earth C plus A. So C implies A. So assume that theta hat splits. And let's P be the splitting. Okay, so we have this map. We have this glorious map that exists after we complete. Yeah, so let's take M to be an R module whatsoever, right? Why am I taking M? Because what we want to prove is that eta M from M to S tensor M is injective, right? This is what we want. So I'm taking M to see if this is injective. So we want to show that this is injective. And so we want to translate this or to transfer this to the completion, right? Because it is there where we have tools, i.e. phi, to do that. So is it true that we can just complete or, you know, base change by the completion, to be more precise? Is that something we can do? Yes, because R to R hat is faithfully flat, right? Therefore, proving that something is injective can be done after base change by completion. So let's do it here. Well, it's right here. It's the exact same hypothesis. I won't even erase it. Since this is faithfully flat, it suffices to show that R hat tensor eta E, which is a map from R hat Rn R hat tensor R tensor, sorry, S tensor R tensor N is injective. So, but question, how do you do that? Would there be, by any chance, a map that goes from here to here that would work as a splitting? What do you think? Is there a map from here to here that I can use? I think, yeah. What can I do? So, how can I go from here to here in such a way that the composition from here to here is the identity? So the idea is to prove that this is injective. But what we can do is actually split it, and therefore to guarantee its injectivity. How to do that? There is a composition of maps. So we would like to use phi. Right? Phi is this thing that is given to us. So phi tensor m, right here we can have phi tensor m, which would be phi goes from s hat to r hat, right? So over here we would have s hat tensor m. Right? Is there a way to go from here to here? There is, right? There is a canonical way to go from here to here, which is the thing, right? Because S hat is both an S algebra and an R hat algebra. Therefore, it is an algebra over this ring by the universal property of the tensor product, right? So from here to here, I'm going to take that canonical map I'm talking about. I'm just going to put it canonical tensor m. So I can go like, and since everything is just actually is different ways to look at the scalar actions, this whole map here is commutative. And therefore, this thing here is not injective, it's not just injective, it is a split. Right? So that's the proof. Any question with that? Have you Zoom? And so with that in place, well, we're going to have a cascade of consequences for F purity and F splitness, which we haven't defined. So let's get that out of the way right away. So definition: if we have R and FP algebra, so is F pure respectively F split if and only if well, what do you think it is? F to the E R to R is pure respectively split. If the Frobenius map is pure or split, then you say that the ring is a pure or split. Does that make sense? And notice that I just put F to the E. What is the reason? Because it's the exact same thing if you declare that for some or for all of them. So I'm just gonna say sum is slash all E, and so it is an implicit exercise that you have to verify that. is the same thing to ask that for some E, for E equals 1, or for all of them. It's very simple to do that. Okay. So yeah, we got to define our first F singularity. It's just that. And so the first question is like, what is the relationship with regularity? So. Are regular rings F-pure? Well, regular rings are those rings for which Frobenius is faithfully flat, and faithfully flat implies pure. So the first corollary that we get is that all regular rings are F-pure. Right? Again, Kunz's theorem says regular equals Frobenius is faithfully flat, and faithfully flat implies pure, therefore they are F-pure. If a split implies F-pure because a splitness implies purity, right? Question: is a regular ring of a split? Is a regular ring of a split? You may be tempted to say yes, but actually it wasn't known until recently, apparently, that it was the case. So there's a very recent counterexample that I should add to the notes as soon as I have some time, that says that regular rings are not a split. And this is an example by Rakeya Data and Karen Smith. Like for me, it looks like from yesterday, because it was when I was stuck doing my PhD. So actually, Rakeya and I are the same academic age. We were doing our PhD at the same year. And this was part of his PhD thesis, I think. Yeah, it could be from a bit later, but let's say it's no more than 10 years ago. But yeah, for me, it looks like yesterday. It could be from 2000, what? 20, something like this. Okay, but this to me crazy that it was open for so long. And actually, their example is for Italian dimensional one. They constructed an excellent discrete valuation ring. Therefore, use regular dimensional one. Excellent, even excellent. It's not definite. That's the whole point. Where it's not a specific split. Actually, I think it's something like its Hom set is even 0. There are no Hom. Its Hom from Frobenius thing is 0. There's not even a chance for anything to split. It's a pretty crazy thing. It's a diabolic ring, of course, but this is the thing, right? Like, if a splitness, I don't think if you can call it an honest F singularity property, if regular doesn't imply it, but if purity is. So that's why we are gonna be calling things F-pure most of the time, because that's the nice notion. And it just happened to coincide with F-splitness in certain setups, which I'm gonna remark right away. So, well, another corollary, let's say, is that R is F-pure if and only if Rp is F-pure for all Rp, which actually, if a split doesn't satisfy, it's not true that you can just check the split locally, right? So geometrically speaking, right, what you have, like, so, well, it's true that if R is at a split, then it has to split locally. That's fine. Sorry, for all P, OP in spec art. P spec art. This is fine. You can take a global splitting and you can localize it and you can get a whole bunch of local splittings. But what is the trouble is that if you have a whole bunch of local splittings, they have no reason to talk to each other, so that you can glue them together to a global splitting. Okay, in general, unless, for example, Frobenius is a finite, where we give you a reason for them to glue together, so to speak. Okay. So the other corollary is that suppose that R is either a finite. So you see the first instance where the finiteness is really, really important for this to be nice. Or let's say complete. Either one, then if pure and if splitters are the exact same thing. So usually the strong, well, the most common hypothesis people use is a finiteness. So you see, usually when we are like in this type of setups, we put in our mouth the word pure, but very often we're talking about the splitterness. Because it's like a stronger thing, you know, it's like a stronger consequence. You have a splitting map. Okay. How are we doing with the time, more or less? So those are our first F-singularities. The next step is to know how strong this is. We're going to see that to answer that question, we need this Feather's criterion to give us a good idea of what this could possibly mean. Well, before going on, like I should remark the important concept here, right? Like, so if R is at the split, then what does that mean? That you have Frobenius here. So we were calling this something like this. So it means the existence of phi such that this is the identity, right? This thing here is referred to as an F-splitting. I guess Fe is splitting, to be more precise. And this is what the theory is all about. Okay. So we're going to spend big time probably studying F-splittings. Okay, so this is a thing that goes from here to here, right? And we are going to study this, you know, like very hard. And there would be a trace, this the so-called Frobenius trace. Okay. And all that is going to be part of the game. So what the first notion of F-singularity tells you is that you should put an emphasis on F-splittings. Okay, I wanted to say that. It's complete. One more corollary I forgot to write down, sorry. You see, like all the work we did paid off. Now we're just like, you know, having all these corollaries for free. Corollary, maybe let's write it down over here. Corollary, if you have a local wing, so then R is a pure if and only if R hat is F split. Okay, so that's what if purity means for a local ring. It means that the completion is a split, which is the same to say, right? Like our hat is a pure. So you can see how if purity is stable under completion, meaning that it's a truth, a singularity notion, but if a splitness is not, it's not well behaved. Okay. Any questions with this? Okay, that's the ABC of F purity. And now the important criterion here. I think I forgot one more corollary. Well, it's an exercise. It's gonna be an exercise that is gonna give you a whole bunch of examples. Is that if you have a map of rings that is pure, okay, then this is gonna mean that if S is a pure, then R is a pure. Okay, and the same thing if you put a split here. If you put that you have a splitting thing, this is F split, then R is F split. This is an exercise. Again, like if you have a map of algebras that has the purity or a split property, then you can descend the respective property. So, and this is going to give you a whole bunch of examples. For example, you're going to have that the so-called direct summas of regular rings are pure split. And so this gives you a whole bunch of singular rings that happens to be pure. But let me continue here the example. So what are examples, right? Like you can take S equals polynomial ring, let's see, which you know now that is if pure, if split, right? Both of them. And now you can take direct summas, right? Like, and that's relatively easy. For example, you can take the so-called Veronese, right? Like this ring is graded, right? It has a grading over the natural numbers, right? This is just the K-vector space of polynomials, of homogeneous polynomials of degree D, right? And so what you can do is you can take the so-called Veronese, and then you get here, right? S and D, where D goes into them, you get these multiples, right? And so by definition, this is a direct summa of this ring. So this is split. And therefore, this is a singular ring that is F pure. So if purity is weaker than regularity, that's what it shows. So for example, you can take K, X squared, XY. This is the second Veronese of the polynomial ring in two variables. So here you have a singular ring that is a pure. But for example, you can also take the Segre product of two polynomial rings if you know what that is. It's another direct sum of regular rings. So that's the point, right? Like there are a whole bunch of rings that just happen to be direct sums of regular rings, right? For example, you can take groups acting on the polynomial ring, and you know that there are all these conditions that guarantee that the ring of invariance is going to split from it. And therefore, all those are pure, and so on. Yeah, I guess fetish is gonna be for next time. Sorry, we're almost out of time. Well, let me give you one more example. I mentioned Segre products. What is a Segre product of two polynomial rings? So, well, let's say that you have a polynomial ring in X's. You can take its product with another polynomial ring in the Y's. Let's say you have maybe n up here, n here. You can say that this is, well, this is by definition, so it's going to be a big direct sum. And what you do is that you take the potential products of the x's of degree d with the y's of degree d, right? And this lives inside as a direct sum inside the polynomial ring with all the variables. So that's another direct sum of a regular ring. But this is singular. This is very, very much singular. This is a determinantal ring, right, and two minors and so on. But I don't know if you have seen that, so maybe I shouldn't say too much.
Are homogeneous polynomials pure?
Homogeneous polynomials. Well, they don't form a ring. So you can take a polynomial ring and you can decompose it as a direct sum of homogeneous polynomials, but each summand is not a ring on itself. So they cannot have the property of being a pure split. Yeah. So any questions? We can stop here, I think. So next time we're gonna study Fedor's criterion. We're gonna prove it, and everything's gonna be great. And I hope the point of the Fedor's criterion is gonna tell you in practice how you check if a ring that is presented to you as a quotient of a polynomial ring is F-split or not. And then you're going to have a very beautiful characterization that you can use to tell you how rare or how common F purity is. Okay, so